Dear students, can you imagine a life without electric power? Just think about it, right? So, it is very important to know how do we get electric power, how it is generated, what is the principle, who invented. All these things are going to be really interesting, right? That we will discuss in this chapter. And this is chapter 6 of class 12 physics part 1, and the chapter is electromagnetic induction. Let us learn some basics before entering into the major concepts, right? First one is area vector. I think the diagram itself gives you a clear idea about it. There is a surface area whose area is capital A, and the area vector corresponding to this area is taken perpendicular to the surface, and it is represented by A vector. And that's what the definition says: the vector of a plane surface whose magnitude is the area of the figure and whose direction is that of a perpendicular to the plane of the figure. That is, area vector is always perpendicular to the corresponding area. Another important term is magnetic flux, and also we will discuss about flux density, right? But first let us understand what is magnetic flux. There's nothing but you can remember the electric flux definition in chapter 1. Number of electric lines of force passing through an area. Similarly, the number of magnetic lines of force passing through a certain area is known as magnetic flux. And what was the equation for the electric flux? If you remember, that is phi is equal to E vector dot A vector. Here E will be replaced by magnetic field, so it is phi is equal to B vector dot A vector. And of course, if you expand this, it is going to be BA cos theta, where theta is the angle between the magnetic field and the area vector. Remember, the area vector is always taken perpendicular to the corresponding area, because many students do mistake even in the board exam. Okay, they learn throughout the year, but still they are forgetting about this area vector. They consider only the area, they are not considering the area vector, right? But we have to consider only the area vector. So look at the first diagram. The magnetic field is horizontal and towards right, and there is a surface area taken which is perpendicular to the magnetic field. Then what about theta? Immediately don't think about 90 degree, it is going to be 0 degree, because the area is perpendicular to the magnetic field, but the area vector is parallel to the magnetic field, and therefore theta is 0, and hence magnetic flux becomes BA, that is the maximum flux through the area. And the second diagram, the area is parallel to the magnetic field, but the area vector is perpendicular to the magnetic field, and therefore the angle between them is 90, and cos 90 is 0, and flux is 0. It is very simple. If the area is parallel to the magnetic field, none of the lines will pass through the surface. They can either pass above the surface or below the surface, but none of them can pass through the surface, and that's why the flux is 0. Very easy, right? And third diagram gives the area which is in a different direction, where some angle is there between the area vector and magnetic field. Here we should apply the formula phi is equal to BA cos theta. And this magnetic flux is also a scalar quantity as like electric flux, but its unit is Weber or Tesla meter square. As we all know, Hans Christian Oersted, who made an important turning point in the field of electromagnetism. He found that a current carrying conductor produces a magnetic field around it. And later, Michael Faraday thought in the reverse direction, that if a current can produce a magnetic field, then why can't a changing magnetic field produce a current? In that way he thought, and he succeeded also, right? And finally he and also Joseph Henry both did so many experiments to demonstrate electromagnetic induction, and finally Michael Faraday came out with two laws for electromagnetic induction. The first law says Whenever the magnetic flux linked with a closed circuit changes, an EMF is induced in the circuit. And second law says the magnitude of induced EMF in a closed circuit is equal to the time rate of change of magnetic flux linked with the circuit. That means faster the change in magnetic flux, more the amount of EMF. And this is what Faraday's second law of electromagnetic induction. If the magnetic flux linked with the coil changes by d phi in a time dt, then we can write the induced EMF as E is equal to minus d phi by dt. Suppose the coil has n number of turns and tightly wound in such a way that each turn covers the same area, and therefore the flux through each turn will be the same, and hence the total EMF induced in the coil will be n times the EMF induced in a single coil, right? And therefore E is equal to minus n times d phi by dt. Everything is fine. Why is this negative sign coming throughout? What does it indicate? d phi by dt is the magnitude of induced EMF. N times of d phi by dt is the total EMF induced in the coil. But what does this negative sign indicate? Let's see the answer. Here is the answer for that negative sign in the equation of induced EMF. It is because of Lenz's law. Have a look at this physicist, Heinrich Friedrich Lenz. He states that the polarity of the induced EMF is in such a way that it tends to produce a current which opposes the change in magnetic flux that produced it. Why he said like this? Because he strongly believed the law of conservation of energy. And have a look at the statement. It is very clear. The induced current will flow in such a direction to oppose the change in magnetic flux. The change in magnetic flux is done by some external agency. And if this induced current opposes the change in magnetic flux, the external agency must continue to do the work, and that work will be continuously produced as induced EMF, continuously converted into induced EMF. If the external agency stops the work, the induced EMF will also be stopped. And this is how Lenz believed that the induced current will always opposes the change in magnetic flux. Let us understand Lenz's law by some illustrations. Before that, have a look at this diagram. There are some conductors AB, BC, CD and DA, but actually AD, DC and CB are fixed firmly, but this AB is a movable conductor. It can slide over, right? And you can see there are cross marks. I told you already, the cross mark represents a magnetic field which is inward, that is perpendicular and inwards. AB is the movable conductor. In illustration 1, that AB is not moving, and therefore the magnetic flux is not changing, and hence no induced current. And in illustration 2, let us see what happens if the conductor AB is moving towards right, and the existing magnetic field is B, which is inward magnetic field. And if the conductor AB moves towards right, what about the magnetic flux linked with the closed conductor? That will increase because the area increases. When AB moves towards right, area enclosed by the conductor increases, and therefore magnetic flux also increases. So the inward magnetic field increases. So what is the cause here? Increasing magnetic flux. Direction of this is inwards. Okay, what should be the direction of the induced current? As per Lenz's law, the induced current should flow in such a direction to oppose the cause. The cause is increasing magnetic flux. So what should be the nature of the induced current? It has to decrease the magnetic flux, right? So it has to produce a magnetic field in the opposite direction. That is, inward magnetic field is the cause. It is increasing. So the duty of the induced current is to decrease this flux. In order to decrease the inward flux, the induced current has to produce an outward magnetic flux, which are represented by the red color dots. You can see that, right? Okay, to produce an outward magnetic field, in order to oppose the cause, what should be the direction of the induced current? Should it be in the clockwise direction or should it be in the anti-clockwise direction? To find the solution, we use right hand palm rule. You can see that the four fingers are folded, but the thumb finger is stretched. If the thumb finger represents the magnetic field, the direction of other fingers represent the current. And if you keep your thumb along the direction of this outward magnetic field, what would be the direction of the other curled fingers? Will be in the anti-clockwise direction. To check, you can keep your palm on the screen and check. So keep your thumb along the direction of the outward magnetic field and other fingers will be in the anti-clockwise direction. They are curled but still will be in the anti-clockwise direction, and that is why the induced current is in the anti-clockwise direction. In illustration 3, the conductor AB is moving towards left, and of course the area decreases. If area decreases, the cause, that is the inward magnetic flux, also decreases. What should be the role of the induced current? It has to oppose the cause. Cause is decrease in flux, so induced current should increase the flux. How can we increase the flux? If a magnetic field is in particular direction, how would you increase the flux? By producing another magnetic field in the same direction. So this induced current produces another magnetic field, but this time it is in the same direction of the existing magnetic field. So the magnetic field produced by the induced current is represented by the red color crosses. So clear, causes decrease in flux, but the induced current has to increase the flux. To increase the flux, it produces another magnetic field in the same direction, and hence it is obeying Lenz's law. Okay, for that, what should be the direction of the induced current? Again, you have to use the right hand palm rule. So keep your thumb along the direction of the induced magnetic field, that is red color crosses. What is the direction of the red color crosses? It is also inward. So keep your thumb finger along the direction of the induced magnetic field, that is inwards, and see the other four fingers, they will be in the clockwise direction, and that is why the induced current is flowing in the clockwise direction. It is very simple, but make sure that you are using your right hand. Sometimes I do see students are using their left hand and they go wrong, right? Okay.